Hi, my name is Chris and I'm a postdoc within ML4Q, and you are listening to ML4Q&A. In this podcast, members of the Matter and Light for Quantum Computing cluster talk about their research as well as other topics and the future of quantum. In today's episode, I'm talking to david.gross about his career path, advising student projects in theoretical physics, teaching quantum mechanics, and the Google event he was probably never invited to. David is a professor in Cologne and a vice spokesperson for the cluster. He worked with Jens Eisert in Berlin and followed him to Imperial College in London to do his PhD. Then he did postdocs with Reinhard Wörner in Hannover and Matthias Christandl at ETH, became a tenure-track professor in Freiburg to ultimately become a professor in Cologne. He's known for work on random matrix theory, compressed sensing and measurement-based quantum computing, and more generally work in finite phase space. But probably he's most well known for asymptotic freedom and having famous PhD students like Edward Witten and Frank Wilczek. So David, when did you decide to become a theoretical physicist? What was your gateway drug into this business?
Yeah, hi Chris, good to be here. Maybe we should explain the Frank Wilczek joke at some point of time. I'm not sure everybody got it. How did I become a theoretical physicist? Oh, I don't know, when do I start? So, right, if I go way back, then I have to first say that I'm very suspicious of people who know what they want. So it's not that I decided to become a theoretical physicist early on, but I don't know, I finished school and couldn't decide what to do. Luckily, I had like a year of social service still, but then I still couldn't decide what to do. Then I started an engineering class and I quit. I started computer science. At university, I quit too. I studied a bit of German literature and then I switched to physics. And and then it was too late to change track. But it was not a very deliberate decision, kind of, I got sucked into it.
That's very nice. And I guess this engineering background is also not so bad. I mean, even Dirac started in some ways in engineering, right? Did the engineering influence your early physics thinking?
I think so. They say that the other grass is always greener. So sometimes I meet with engineers and sometimes I work with engineers. And I'm always super excited. So, we have a project and then what we do, can be used in mobile phones. How cool is that? And they go like, oh, what we do can be used in quantum information. How cool is that? So, but definitely, I kind of miss building stuff and having something at the end of the day you can touch. It's something I'm always excited about.
Did you have like a lecture or something that you had and afterwards you were like, okay, I want to become a quantum physicist?
So definitely there was like a well-defined time when I quit engineering and decided to enroll in physics. This is a very clear moment and I can tell you exactly what the problem was. So I was sitting in an electrical engineering class and you would compute the capacity of a capacitor. Right? And you do it by integrating the field strength between the two plates, right? And then you get a value. And if you want to do it, you have to smear out the charge equally over the plates. But then there was little David sitting in the lecture theater thinking, in actuality, charges are little points. And so this approximation to smear it out, it's not okay. So if you then calculate the integral between a point charge and a point charge, you always get infinity. And so I was confused because there was an inconsistency in our theoretical understanding. So I went to my professor and said, I don't get it. I did the calculation differently. I get infinity. So what's up with that? And he was very patient and thought I was like the stupid student and was like, but it's a capacitor, so you have to calculate it like this. And I say, look, I'm not stupid. I get it. I know how to calculate it. But, there is a consistency issue here. Don't you worry about that. And he was like, look, you calculate the capacity by computing this line integral. And then I decided, okay, for our mutual benefit, it's better if I quit, because it's a different way of thinking, So he was thinking how, and he knew how to treat the system, and so for him it was done. And I was thinking in terms of getting more the why, right? In terms of getting a consistent understanding. But if you're an engineer and you want to build the next Airbus airliner, if you know how to do it, you're done. You don't have to understand that the thing that pulls the airliner down is resulting from, the geometry of space-time. It's the wrong level of detail. And so, yeah, after this, I quit electrical engineering, I think for our mutual benefit. So they were annoyed with me, I was annoyed with them. And I think it's been a much better fit in physics. And it took 2 more years before I found in the textbook the little sentence saying, so this infinite capacitance is an artifact of the infinite self-energy of a point charge. And, there was like a side note in some textbooks saying, an unsolved problem of classical electrodynamics is the divergence of the self-energy of the electron. And I felt at home, somebody was acknowledging the problem I saw. They also didn't solve it, but this was fine. I didn't want to have a solution. I just wanted somebody to say, yeah, there's an issue here.
So I guess that really set you up to become a theoretical physicist, because from my experience as an experimental physicist, I often stop at the point where the model that I use sort of just describes the data that I have. But indeed, there's often conceptual problems that come in, and I usually stop at the point where I get convergence and don't worry that much about it. But I think we need both kind of ways of thinking.
I think, it's a bit the how versus why distinction at play here too, right? And I think there's the reason for both. Let me be clear. It's not that I think the why thinking is better. It's just, both is important. Like, the engineer who actually worries about general relativity will suck as an engineer. It's not a good way of thinking if you want to, get the thing through the door.
So then you did a PhD with Jens Eisert and your diploma as well. So that basically put you into the field of quantum information and many-body physics from the start, or?
Yeah, this was actually the other way around. I was studying at TU Berlin, and at the time Jens had his first junior appointment in Potsdam. So I decided I wanted to do quantum information. I was looking for somebody who could, advise me. And there was, within 50 kilometers, there was only one person, who was Jens. And so I drove out to Potsdam, which was a different university, and I said, I want to do a thesis here. And then he said, yeah, that's cool, but I don't have capacity. So sorry, I can't do it. And then I just didn't go away. I think I was a bit annoying, actually. He was just saying, look, he was very polite, of course. He was saying, yeah, look, sorry. And I was getting angry because I said, look, this is not how it works, You are a civil servant and, you're paid to do quantum information. You're the only one in the region to do it. So you can't just say no to a student, that's outrageous. I don't think this way anymore, but at the time I did. And I just turned up every day. And at some point he just gave up and said, okay, fine, here's a thesis.
And you then followed him to Imperial College, right?
Right. Mm-hmm.
As a theorist, you do a lot of thinking, right? So you sit around and you ponder a problem until you have some genius idea.
That's right. So I moved to London, and then my grandmother, she was always asking me, so what do you do? And she had no understanding. She had no academic background, so she was completely opaque to her how I would spend my time. And I tried to explain it to her what I did, but she was unconvinced. And then later, my sister translated it to her, and she told her, well, David, he's sitting in his office looking at Hyde Park and he's thinking. And then she felt, okay, that she got. And she never asked again. So your description was pretty much spot on. Yeah, you sit there and, think.
I find it amazing, these kind of theory PhDs, you tackle problems that are generally unsolved. And there's maybe not always a hope that the problem that you're working on is solvable. Like, how was your experience there? Did you just have a lot of problems and you got lucky in finding always ones that were solvable, or did you have a lot of problems that...
Right. I think it's much easier for a theoretician, by the way, than for an experimentalist, because you also tackle things that are generally unsolvable. But for you, it takes years to find that out. For us, it usually takes weeks, right? And then we can pivot to something else without needing like 5 million euros of investment. So I have much higher respect for experimentalists. But it's, of course, a legitimate question. There's a very thin line between trivial and unsolvable in theory. So every problem you can come up with is likely unsolvable, completely hopeless, completely beyond our understanding. That's generically true. And if you're very lucky and have something that can be solved, it's usually trivial. And to find even a question where there is a legitimate hope that it falls in between these two extremes, it's a very difficult problem. Maybe the most difficult. I think asking the right questions is much harder than finding answers to it. It's, by the way, also what we see in advising students. They can solve problems, but to identify problems, that's much harder. They can learn this much later.
That maybe gets to the core of my question, because you have an advisor, Jens Eisert, who you go to and you say, I think this problem is interesting. Okay, and then he says...
Okay, so then, of course, this is, I think, this is the primary service, I think, of a theory academic advisor, is selecting a problem. That is the service they provide. And so in my case, it was also very clear from the very beginning. Actually, we started with my PhD, continuing with the same problem that also started my master's. And it was on a paradigm of quantum computation that had just been recently discovered back then and was very much hyped, and it's still important, and it's called measurement-based quantum computation. Maybe I can explain that. So a computation we think of as some dynamical process, right? Think of, like in one of these mechanical computing machines you can find in the museum. No, you set the input, and then levers move, and this somehow processes information, and in the end, some light flashes, and there it is. So you can now ask, so where has the computation, where was it done? And it's natural to, identify it with this dynamical process of, one lever hitting the next and, some current being triggered, I don't know. And so this dynamical picture is also how we started to think about quantum computation. So what is a quantum computation? It's a sequence of modifications of quantum data, and a modification is here a quantum gate, so a well-defined unitary time evolution. But you would also think about it in this, consecutive processing kind of way. And then there was a huge discovery by Hans Briegel and Robert Rausendorf in early 2000s that you can have a much more static setup, and it has the same computational power. And so the setup is this: you take one quantum state of a many-body system, and you do nothing but perform local measurements. So you take one particle after the next and you measure it. And based on the measurement outcomes, you select what to measure next and which particle and in which basis. But there's no dynamics anymore. And they proved it was equally powerful, right? And that was conceptually, this was a big breakthrough just because, it felt completely different. The entire term of quantum information processing, the processing is a dynamical thing. But, it somehow had the same computation power without the ing term. No, there was nothing being inked. It just sat there statically and you read out the result. And at the time, there was only one example known of a state that had this power. It's a so-called cluster state, nothing to do with the cluster of excellence, but it's called the cluster state. And so, the question I got asked on day one of my master thesis, or diploma as it used to be called, was, that's weird. It's unlikely that there's only one state. Find another one. So that was the question. And in my diploma, I did not find one. So I did not. It was still like a 1-year thesis back then, and I had 1 year and I couldn't find one. It was also one of these open-ended questions that students are usually bad at. It was not calculate this function and plot it in the interval of which that's how I start a master thesis. I give something like this so that people don't fail, and then if they do it in 3 weeks, we can still move on to the more conceptual ones. So I got asked this question, and I think it was too hard for me. I don't know. I didn't have the tools. I didn't even know how to get started. And so it's interesting because what I did then is I kind of got sidetracked. And I read this old, Rausendorf and Briegel papers, and I found, they use this language of what we call today, stabilizer codes, which are used in fault-tolerant computation. And there was some open problem there, and I kind of got sucked into this and ended up writing my thesis about a completely different question than what my task was. But then we revisited it for the PhD, and then we found new models. And now you're saying, what are you known for? And I think what I don't know if you want to talk about this. What I was known for in the beginning was, we were the people, or my advisor and me, we were the people who could generalize the cluster state and find new models. But okay, so to summarize your question, so there's how do you find projects? So there's and do you have many or not? So here's the answer. So one, it's the primary task of the advisor to select one, and I was very lucky in being provided with a question that a lot of people were interested in. So when we did succeed, suddenly a lot of people were interested, and one that was eventually solvable, even though it wasn't maybe solvable in the beginning. But also you get stuck. And then you have the privilege as a theoretician that you can just, pivot to something that is kind of related and, prove yourself there and answer the question there. And, no major investment is necessary. So the answer is both. The advisor selects, but also you have probably many of which most don't work and a few do.
So cool. Just a comment from me about your career path. You started with Jens Eisert, and then afterwards you went to Reinhard Werner, right? Mm-hmm. And maybe this is my impression of them. I've not really met either of them, but I've read a little bit of their work. And I would say that they seem very different people. Like with Jens sort of being on a more pragmatic side of the spectrum, and Werner being like a very philosophical almost guy. Did this really influence you at the time? Did you make this as a conscious choice?
Sure, of course. Yeah, no. It's funny that you call Jens pragmatic, because of course he's also, one of the, theoreticians who's more removed from the dirty business than most people are. So on the spectrum, he's already pretty far on the mathematical side. But of course, Reinhard is way out there. You said philosophical. Primarily, he's just an old school mathematical physicist with a solid education in functional analysis and publications in functional analysis journals, who understands his operator algebras. And of course, they work extremely, extremely differently. Right. I mean, being a bit torn between, more pragmatic approach and more mathematical approach is something that I've always been. And so I wanted to, after the PhD, I wanted to test, how I would harmonize with, an honest to God mathematical physicist. So it was a conscious decision, and I think it was good to learn both styles. They are extremely different along many various axes, of the human existence, and mathematical versus pragmatic is one of them, but there's many more.
Maybe to finish this section about your sort of formative time, what do you enjoy most about the work? And from the PhD to now, how has your work changed?
What I do enjoy most, I mean, this nerdy experience of getting something, I think that's why we are in business. If not, we could go to industry and earn much more money. It's, sitting down and looking at the hard problem and seeing how your understanding chips away on it and makes it easier and easier and clearer, and suddenly, bang, you have a nice picture, and ideally you can use your improved understanding to now do things that other people failed before. This is a choice why we do it. I can't see any other reason. Maybe a few, but that's the main one. And how has it changed? Well, of course, as you grow older, you get further away from the actual dirty work of actually tackling hard problems, and you're more moving into or being pushed into, I don't know, a bit of both, a management role. And everybody complains about this. Few people do something decisively about it, which of course means maybe the complaints aren't honest. I don't know, but I would also complain about it. But also I don't do anything decisively about it, so maybe I'm not honest to myself. I don't know.
So then maybe you already said management, so we should maybe talk a little bit about ML4Q. So how did you get involved with ML4Q, and what is your role in the cluster? And how do you see science management maybe then in the broader context?
Oh dear, that's a big topic. You see, this excellence initiative is extremely important for universities. It's how they define their profile, how a lot of funding goes to the university. But it's not just that. It's not actually primarily about funding. Germany has a weird education landscape that is very much unlike, I think, most other successful science nations. In that, in Germany, traditionally, there was not a big difference between the universities in their perception. It really didn't matter which university you attended for your further career. Just compare that to the US, where at the age of 17, or France, for example, or the UK, where at the age of 17, a major shift, people get sorted into tracks. Adult university, second tier versus, community college, I don't know. And we didn't have that, right? And this egalitarian system in Germany had many advantages and many disadvantages. The big advantage is that, 16-year-olds don't spend time, on fake extracurricular activities so that they can impress some admissions officer. So we don't, waste our time when we are 16 on this. There's also negative sides in that it's very difficult to attract the top international researchers because they want to work at a top international school, and the US has them. In Germany, not so much, and certainly back then it didn't. Okay, so there was a political decision that we should move away from the German egalitarian system and designate, some universities as being, more excellent than the rest, and the downsides were deemed to be less important than the potential upsides. So I'm saying all this because, to explain why this is such a big thing. So I don't think it's actually about the funding primarily. Of course, it makes a lot of things possible, but it's about being, in this race that now started, you want to be in this elite pack of universities who stand out. It used to be called, the word elite used to be used. It kind of like people discontinued it in favor of excellence, but Elite-Universität used to be the term. Okay, so then, of course, when, the next round of the Excellence Initiative showed up on the horizon, everybody was asked to consider what do you have that is competitive. And in Cologne and in the region, in Aachen, in Bonn, in Jülich, there has been a lot of investment into quantum science in the years prior, and we felt now we had a critical mass, and the topic excited people, and also we didn't collaborate so closely in the past, but now we could say, a lot of new people had been hired recently, so we could, make a case that, things have changed and now was the right time. And so it was just, from a political perspective, it was just clear that this is one of the topics where would have a chance of being successful. And so then all the people who could naturally contribute to it got together, and I was of course one of them. Right, so that's how I got sucked into it. And yeah, what's my role now? I don't know. There's different hats I have on my head. There's some science to be done, but also I'm also involved a lot in just steering this big tanker. There's a lot of it's still a very big project. No, there's tens of millions of euros that are being spent over the project period, and we are accountable to the taxpayer. And so they need to be well spent. Yeah, there's this cycle of science funding. No, first you don't get to do research because you have to write a proposal, and then when you're lucky you get the money, and then you don't get to do research because you have to spend the money in a way that is sensible. It's a lot of work.
So, and Jülich might become a quantum hub. I don't know what's the political status of this, but let's say they will have a larger quantum computer. Yeah. Would this be something exciting for you to play with from a theory side, or?
Right. Okay. So that's now a completely different set of questions. A very important topic, because we're seeing an enormous change of the character of the field. I was talking with Dagmar Pruss on the phone just yesterday, where we reiterated this point. When I started only 10 years ago, it's not such a long time ago, or a bit longer. Quantum information was kind of like the absurd spinner, crackpot-y adjacent pastime that people kind of, I don't want to say laughed, but certainly it wasn't at the center of physics. Yeah, and this had advantages and disadvantages. The obvious disadvantage is that it was very difficult, for example, to get positions for the first people, right? Because there was no, quantum information labels on faculty position. Totally different situation today, where you have trouble recruiting, but back then this was a big problem. But also it meant one had a lot of freedom. Yeah, because all the serious people weren't really looking too closely, and one had a bit of freedom to explore something that was completely novel. And Narrenfreiheit, I don't know how to say that in English. No, the freedom to explore without being held to the standards of a professional. Okay, and this is now changing completely, and it's changing very fast, and it's changing in the last 3-4 years, maybe not longer actually. And now the big industry players are moving in, and the big research centers are moving in, and the big, politically savvy people are becoming important, and they are guiding millions and hundreds of millions, and the orders of magnitudes of funding has completely changed. And again, this comes with advantages and disadvantages. So the advantage obviously is now suddenly, it might become real. And in a way, again, funding is actually now minor, less of a concern. If you have a good idea, you'll get the money. Maybe not easily, but it's not impossible now. Yeah, but also it changes the character of the field a lot. There's a lot more pressure on, having results and being practical. And again, the kind of questions change. Before, if you found the most elegant mathematical thing, this is, how you got credibility in the community. And that's a bit irrelevant now, because now it's an engineering problem. So it's not like the most elegant construction for an asymptotic code, but it's, this machine, it has 200 things, and this error model, now do something. The output is not an ideal Platonic model. The output is a bunch of numbers. Yeah, so it's very different, and I'm a bit torn. It's obviously it's fantastic. I know it's great, but also there's a bit of a sentimental side to me that kind of looks back at the good old days when we could,
Yeah, what I find interesting about your work and this noisy intermediate scale quantum computers, which is basically somewhat crappy quantum computers, right? Like they are not good enough to, let's say, factor a number, but they are maybe good enough to give you some output that is hard to achieve classically.
Okay, so SCQC instead of NISQ.
Yes.
Somewhat crappy quantum computer.
Yes.
I like that, yeah. Okay. Not completely shit.
But these systems are mathematically quite interesting, and a lot of the work that you have done on a more mathematical side, I would say, becomes very important in these systems, right? Can you elaborate on that?
Okay, I'm not super sure that's true, that a lot of work I did becomes very important for those, but I agree with you that there's a lot of non-trivial mathy questions also about these NISQ computers. And in computer science, there's two contradictory or two, complementary approaches. You can design algorithms, or you can try to prove that algorithms don't exist. Yeah, it's a very different skill set, by the way. Totally different people working on this using totally different methods. And now if somebody, puts you in front of the console of, a 200 qubit noisy quantum computer, suddenly you have two things you can spend your day with. You can either try to say, okay, let's see, what can I do with it? These algorithms that are well understood, like, factoring, but it's completely hopeless. So then there is heuristic problems where it's plausible that the thing might be of utility, for example, finding properties of quantum chemical systems. Yeah, and you could try to improve that and try to, design algorithms that, will likely use the power of that computer. But you probably can't prove it, you know. It's very difficult to prove that you have an advantage. It's very difficult. So it's probably the gap is not big enough. So you end up running heuristics, and there's always the risk that, you know, whatever quantum chemical system you manage to run on this computer, somebody else comes, you know, calls you a day later and say, I have my iPhone and I found a new algorithm, I can now also do it. Yeah. Or you can spend your day trying to do the opposite and be like the spoiler or something. You know, you can try to prove that the computer in its current iteration can't actually outperform a state-of-the-art classical system. And in particular, in the second. No, I don't know, in both. There's interesting math in both. Maybe there's more rigorous math in the negative approach, actually, right? Because so how would you prove that a quantum computer, a noisy one, is of no direct value? You would find a classical simulation for it that's efficient. You know, if you could do this, it's game over. So there, I think there's many interesting questions. And in particular, because here's, by the way, what makes it hard. What makes it hard is the role of noise. In particular, correlated noise. I think that's very interesting, no? Because correlated noise has two contradictory effects. One, it induces correlations because it's correlated noise, and tracking these correlations might be difficult. Yeah, but two, it's noisy. And so noisiness means it becomes more classical, so it should be easier to track on a classical computer. But the correlation makes it difficult. So how do you balance the two against each other? So there's very interesting questions about this.
Is there a problem in the quantum case? Because the kind of correlations that you can have in a quantum system are sort of a little bit more complicated than what you could have in a classical system.
Yeah, well, okay. So I don't think that's super relevant. So of course, you know, in quantum systems you can have, you know, these bell-like correlations, which are, you know, the source of all our excitement about the philosophical impact of quantum theory. But it's not the same kind of correlations that I mean here. It's you know, you have an impact, some noise impacts one qubit, and then the next gate is an entangling qubit, and it will delocalize the effect of the noise, right? And this is, you know, it's not the kind of correlation that allows you to violate Bell inequality, but it's the kind of correlation that makes it hard for you to error correct or to classically simulate.
Yeah, exactly. I mean, the error correcting code are based on some sort of redundancy, meaning if you have noise that sort of has the right symmetry with respect to your redundancy, I guess you are never protected from it. There's certain kinds of correlated noise that you can just...
Yeah, that's always true. Yeah. I mean, an error correcting code can only work against, you know, a given model of noise, and if, you know, real system does not comply with that, then good luck. Yeah, sure. Mm-hmm.
Just to talk a little bit about benchmarking. So if you want to benchmark a quantum computer, so you have to sort of come up with something that you can efficiently classically compute. And there usually this Clifford group pops up again and again. And then on the other hand, you need to do a lot of statistical analysis to show that the thing that you measure in the end, which is lots of zeros and ones, actually converges or gives you a meaningful value that really relates to a sort of error syndrome that you want to find, or the goodness of your quantum computer. Do you think there's a lot more work there to be done? Will there be still theoretical breakthroughs, and will the small quantum computers help?
Okay, yeah, so it's a topic I worked on a lot in the past, and there's in fact various different problems. You know, how do we verify that a quantum computer does what we expect of it? Yeah, and how do we, if it fails to do so, you know, how can we find the precise way in which it fails? Yeah, and the first one is difficult because, I mean, a priori it's not clear that it works because we have weak classical machines that should certify a strong quantum machine. So that raises fundamental problems. Is that even possible? Can a weaker machine certify the workings of a stronger machine or not, and under which assumptions? So that's very interesting. I think it's partly this is a theoretical problem. I don't think these very hard theory questions are super relevant to practical implementation. There was a breakthrough like 2 years ago, you know, of a paper that, you know, showed how you can, under, you know, mild complexity theoretic assumptions, prove that a quantum computer does something non-classical. And then, you know, a guy from this German computer magazine CT called me and wanted to get an explanation because they wanted to write this article saying, you know, now we can finally trust quantum computing in the cloud. And in the end, he did not publish the article because, you know, we had a very long discussion, and he was a bit disappointed because in the end, the result was way more technical and maybe less practically relevant than he thought. Yeah, so I think the certification business from a practical point of view is not so super important because, the question is, can you trust the output of your quantum computer, for example? This is not so very important because in the end, if it starts solving your problems, if it starts, computing ground state energies or, spitting out factors of RSA keys, then you don't need any theory anymore. So it's a very pragmatic test.
So you're not going to start a startup to advise early quantum computer how to do this?
Well, there is such a startup, by the way, but people I know quite well. But they actually solve different problems then. So the first problem is, in principle, how can I convince that my quantum computer does what it's supposed to be doing, and somebody who's operating it in the cloud doesn't sell me a fake service where in the end they use their iPhone to simulate all my inputs, and if not, they just guess if their iPhone can't do it. So this, I think, is very interesting theoretically, but not so super interesting practically. Practically, of course, it's more down to earth. You have a quantum system and you have some primitives that you think you know what they do, but probably they don't do this exactly. So how can you certify this? And this is very much, it's an engineering problem. Yeah, and it's easy for classical computers because the components are gates, which are very simple objects. Yeah, I don't know, an OR gate has 2 inputs and 1 output, and the output is 1 exactly if the 2 inputs are 1. And there's 4 different inputs, and you can just test them and they either work or don't. So there's not much to think about. In quantum, the simplest gate is, I don't know, a 2-qubit unitary. Yeah. And this has, if you know it's unitary, already it acts on a 4-dimensional Hilbert space, so it has like roughly 16 parameters, but you don't know that it's unitary. Yeah, so it actually is noisy, so there's even more, and you can't access them directly because you can actually access only, you can only do probabilistic experiments and you can only gather statistics about it. And now you have this, it's a classical stat estimation problem. You have an inverse problem, that you want to estimate the parameters of your process, and you only have probabilistic access, and more so, your preparation and your readout operations themselves might not be well characterized, so you don't even know what you're measuring, and it just gets very dirty. And this is a problem where I think a lot of consultancy service will be needed because the inverseness of the problem is just beyond the reach of what we teach physicists in general and experimental physicists in particular. And so this I think is a very practical problem where maybe not very super deep insights are left anymore, but I certainly think these colleagues running the consultancy, I don't think they will run out of business.
No, for sure not. So what's your advice to young researchers? I guess like if you go into these kind of startup things, then you have to solve very concrete problems and you lose sort of this, what you talked about before, that you can just get to the bottom of a problem at sort of your own pace in academia. And of course that goes away. Like you have to then get to the solution of a problem on the timescale of experimentalists, which I'd say is like a year or 2.
So how do I advise young researchers? That is something where the answer has changed completely over the past few years. What I tell them today is completely different from what I said a few years ago. Because now you say, there's a difference between academia and industry. But I mean, the most important thing is now there is industry. This didn't used to be the case just 5 years ago. There was no alternative career option outside of academia. And so I think this is the aspect one should first appreciate, that now people suddenly have a choice and they can go to Silicon Valley and earn an enormous amount of money and get food provided to them in the Google cafeteria and still work on quantum, and this didn't used to be the case. So is the daily work there very different? So first I don't really know because of course I've never worked there, but now I talk to many people who do. And maybe it's not actually so clear-cut. I mean, so these big companies, they have deep pockets. They can afford to have a few people around to also, think about problems that don't have an immediate impact on the experimental setup. So I don't know. I mean, the colleagues I talk to who now work for, North American quantum companies, I mean, do I get more time to ask fundamental questions than they? I'm not sure. I'm not sure about this. So, they have constraints in their job. I have constraints in my job. I don't know.
Okay, maybe a change of pace, and we're going to do a few lightning round questions where you have 2 choices and you just choose between those 2 choices quickly. So one or 2. Wow. Let's get started with some non-physics stuff. Okay. Cologne, Köln, or Berlin?
Can I? Oh man. Can I take this? All right, this is close to my heart. Also, my wife is from Berlin. And so, for example, you could ask her, I can kind of tell you what the answer is. Right. Oh, wow. I can.
Okay, let's move on.
There's a lot of baggage in that question.
Kölsch or Pilsner?
Oh, Pilsner. That's obvious. Kölsch is such a ridiculous.
Do you identify as a physicist or as a mathematician?
You're pushing my buttons. You know how to do it. Here's a big secret. I don't, like to talk about it so much, but I'm an applied mathematician with a good physics education. I think that's what describes me best.
Okay. Do you prefer Einstein or Bohr, the man?
I don't know. The team Einstein is a good horse to bet on always.
Heisenberg or Schrödinger, the picture?
The picture? I think I'm more natural a Schrödinger picture person, but I've had enough exposure to operator algebra that I feel bad about it. So when you asked before about the differences between Jens Isert and Reinhard Werner, no, I mean Jens is Schrödinger and Reinhard is Heisenberg. And I'm more Schrödinger, but I think I shouldn't be.
One world or many worlds?
One world, though I have a lot of sympathies for many worlds.
Quick in between, do you think the wave function is real? Yes or no?
I think no is the better answer than yes, but really it's not that simple.
Shor or Grover algorithm?
Well, I mean, there's no choice. No, I mean, Shor is, of course, but Grover would agree, the one is much deeper than the other.
NISQ or quantum error correction?
Here's, by the way, what I thought for a long time, maybe it's wrong. Do you know that error correction was actually developed by, who developed it? Error correction for computation?
Sure.
No, von Neumann. Yeah, because that's partly true because von Neumann invented basically everything there is.
So classical error correction. Yes.
Okay, exactly. So he also invented the mathematical formalism of quantum mechanics, but he invented classical error correction. It was a big thing, People didn't believe in sustaining long calculations classically and without errors because, hardware was buggy. And so he invented classical error correction for computation. And then it got never used because the gates got better. And so for a long time I thought that this might be something that will repeat. That in the end, error correction has a theoretical value as in showing us that we are not just building an analog computer which can't be error corrected, but that there is actually a computational advantage in quantum, but it will not become realistic until we can improve the gate so much that we don't need it. Like in classical computation, it was important to show as a mathematical insight, it was very important, but computing could only take off after it was no longer necessary. So for a long time I thought this. Maybe I'm getting more upbeat about error corrected quantum computers in the end. Yeah. It's certainly, I like this much. It's much more the way I think. Okay, so to answer your question, error correction over NISQ.
So again, let's switch gears a little bit, and I thought that we could also talk briefly about teaching quantum mechanics, because that's something that we can all sort of relate to.
Yeah.
And I sort of have a few of my own opinions about this topic. I just recently was a TA on a quantum mechanics class, and should we as the cluster also try to improve teaching in quantum mechanics, get together on this maybe? And do you think that we can improve teaching by infusing more quantum information into quantum mechanics?
So firstly, let me defend the cluster. The cluster is already improving teaching, of course. We have a lot of activities there, and just as we speak, our platforms lecture on quantum technologies is taking place again. So, we definitely have done our homework here. So then, you're now talking about, quantum mechanics 1, the third semester. You have these young people coming in, and that's why they study physics. And now, the lecture hall door closes, and now you're there with them, and now you got to do something. And so one idea that everybody has at some point of time is, we should do more quantum information-based stuff because it's all low-dimensional, and you can look at the concepts without having to worry about the technical difficulties of, having infinite spaces. Yeah, where a lot of time gets expended worrying about, I don't know, functional analysis that is really irrelevant to quantum mechanics.
Exactly, like in the beginning, students have to learn what is a wave function and how to deal with this.
Yeah.
And writing this down in a very abstract way actually is very difficult.
So look, so I was once fervently believing what you now indicate, that we should throw out all this functional analysis stuff because it's really incidental to the problem and it obscures the essence, and we should teach them the statistical content of the theory from finite dimensional examples. I'm no longer so sure. So one, it caters to my personal preferences, which is always dangerous as a teacher. No, it's a way that works for me, for sure. But one thing you learn if you teach undergraduate stuff is that what is difficult for you and what is difficult for the students are very different things. And the students, they come in and they have an intuitive understanding, for example, of waves. They know, they've like watched waves on a pond, they know what it feels like, and they understand the math because this has been drilled into them. And they are super happy, to solve the Schrödinger equation for wave function. That makes them happy. And if I tell them about statistical stuff and, Bell theorem for qubits, they are much less happy often. Or there's a subset of students for whom that works much less well. What I learned, teaching quantum mechanics at an undergraduate level was kind of to work against my own instincts and not forget the considerable subclass of students who are much more comfortable with, complex functions and the first order differential equation than they are with the statistical concepts and.
So I think there's sort of three broad ways to go into quantum mechanics, right? There's the phenomenological approach to say, okay, there's certain problems that we couldn't solve, and then Einstein came and solved a lot of them, and then other people came and cleaned up the rest. Then there's also the historical approach, which sort of matches, to some extent those two approaches match, but I guess the general teaching style is a mix out of teaching phenomena and how quantum mechanics solved them, and explaining the historical development of the theory. Yeah. And the third concept is, of course, this sort of axiomatic approach to quantum mechanics, where you say, okay, what is quantum mechanics? And you maybe start with something like a qubit, and you say, quantum mechanics gives you the following rules for the time evolution and for the measurements. I think eventually maybe what we just have to do is we have to do all these three approaches.
I completely agree with you. This is how it has to be done. It used to be just the first, and then people wanted to overcompensate and do just quantum information and the last, and I think in the end there has to be a synthesis. By the way, I'm scheduled to start the introductory quantum mechanics in a few weeks again, and I'm going to do it for the third time here in Cologne, and I'm still revising my lecture notes, and I will do it again differently from the last two times. And one thing, by the way, I have included now is that in the first week I will talk about probability theory, which I think is of course baked into the theory, and it's dangerous because people have kind of an intuitive understanding, but it's not well grounded. And I think a lot of trouble understanding, in particular the axiomatic approach, is that people first need to get a good feeling it's not. I don't do Kolmogorov axioms. I don't do it very. But just to repeat again, what is the setup that we use to talk about classical probabilities? Oh, by the way, here's a test I can do, because you are asking me all this question. That's unfair. Let me ask you a question. So what if I say this event has probability 2/3? What does that mean? What's the meaning of a probability statement? What's the interpretation of a probability? People talk about interpretations of quantum mechanics, and there's fights and friendships break up over it and stuff, but a lot of the debate is actually differences in implicit understanding of what a probability means. So it's also something I've already written up in my internal lecture notes for starting in April. Within the first week there will be one page introducing interpretations of probability theory. And I think it's important, and I think many physicists have never really thought about it. So have you? Could you? I mean, you use probability statements all the time. Do you have? Can you verbalize what they mean to you?
I would say I'm a pragmatic on this side. I have to think about this a lot in my experiment, because when I do my experiments, I usually have, let's say, a qubit, and I experiment with it, which means that I actually repeat the same experiment a lot of times on one qubit. Now, what you could also do is you could have many qubits and do the experiment at the same time on many qubits. In any case, you need to do it a lot of times for probability to even make sense. For a single run of the, let's say you could only do it once.
Yeah.
You would never be able to measure a probability that you don't know to begin with.
Somebody comes in the lab and holds a gun to your head and said, okay, Chris, sit down. You have to run an experiment once, and it has two outcomes, spin up or spin down. I'm pretty good at quantum mechanics, says the person. He says, I computed the probability, it's 99.99% spin up. Make your choice. And now if I take you at your word, you just said, oh, but there's no meaning, probability has no meaning in a single run. I only get a single run, so up or down doesn't matter.
No, of course not.
It's probably not what you would do, no? But why? Why? What is the philosophical foundation of that, But I think it just illustrated my point. By the way, you can't resolve that now, because that's a debate where, scholars have fought over for at least 100 years. So, but for example, this distinction, do probabilities only make sense in an asymptotic setup, or do they make sense before that? And if so, how? How do we think about this? These are non-trivial questions, and
Exactly.
and people usually, even working physicists, usually don't have a consistent worldview, and you can trip them up because they make a confident statement like saying, "Oh, your single-use probabilities mean nothing," and then you put the gun to the head, and then suddenly they mean something. Yeah, and I'm not criticizing you. I'm just saying there is a very fundamental question that we use all the time that we don't often have a consistent way of thinking about. And I think that's important, to tell them about.
Yeah, I mean, it's also in experiments. I mean, what we give in the end is often a number and maybe an error bar on the number, if we are good experimentalists. And of course, there's already a lot of stuff about probability that is implied, namely Gaussian.
It's even worse. No, it's even worse, because this is another one of my pet peeves. We've just pivoted from probability to statistics.
Yes,
which is even much worse. It's even much more complicated. There's even more fights about, how to think about statistics than how to think about probability. But probability theory, at least people get some education maybe in physics at some point of time. But statistics is usually completely ignored. This is completely bizarre, by the way. We have a empirical science, and we don't teach people statistics. Which all the other empirical sciences, every other empirical science, they spend a lot of time on that. You go to you attend a psychology class, and they get a much better education, like orders of magnitude better education in mathematical statistics than does a physicist, who like to think of themselves as more mathematically sophisticated, not there. And I claim that the majority of people who publish error bars do not know what they mean.
Yeah, I mean, I have to say that I often... Yeah. I ran into this problem myself when I was working a little bit on trying to make entanglement. And at the time we had 2 qubits and we entangled them and we measured them a lot of times. And from all these measurements of the qubits, you reconstruct the underlying qubit state, right? So, I mean, every measurement outcome gives you a voltage, and you call this voltage 0 or 1 depending on where it falls. Unfortunately, it's even 2 voltages, which makes it uglier because you have to draw a dividing line between 0 and 1 in a 2-dimensional plane rather than a 1-dimensional plane, which is even uglier. It's surprisingly complicated. And then eventually, of course, you have this reconstructed quantum state. And now you have to give error bars on this state. Now, the funny thing is, if you say fidelity of some value, which is sort of the closeness of the state to a target state that you want, let's say. As you get towards high fidelities, of course, your error bars don't make complete sense anymore. Let's say you have a 99% fidelity. You can't say 99 plus minus 1%. That sort of starts to become a bit fishy.
Yeah.
I have to say, as a dumb experimentalist, we sort of bootstrapped our way around this. We looked at it and we tried to give asymmetric error bars. But indeed, I would say that for experimental physicists, this is a huge challenge. And there's maybe not a good way to get help with this. Because if you go to a theoretical physicist and you want help from them, you usually need to find an interesting problem. And these problems of statistics, they are interesting problems, and they are often subtle and quite difficult.
And in statistics, even the theoretical physicists don't understand the theory. So you probably have to go to, I don't know, an economist, actually.
Yeah,
go to an economist.
Exactly.
No, I mean, I'm not kidding you. Economists, they have the quantitative education that they can teach it to you. The psychologists maybe know more stats than we, but maybe they can't, use the right language. As, I'm not talking about an individual psychologist, but, as a, property of this class of people. Yeah. But, go to an economist. That would be my advice if you want to know.
No, it's a good point to segue into another topic that I have in my notes here. Maybe to finish off, like in this teaching of quantum mechanics, should students learn about Bell inequalities?
Oh, absolutely. Yeah, sure.
Which is often sort of a topic that is skipped, right?
It's the topic that is skipped because also I think many working physicists can't teach it very well just because they never learned it and it's not part of their daily work. And it's also, how to teach this, by the way. There are also very strong opinions about. Maybe we can talk a bit about it. Because I think it's also often taught not in the way I think it should be taught. So one thing that is very important about Bell inequalities is that it's not about quantum mechanics. But to even get this into people's head is difficult. So often when you read an account by a physicist about Bell inequality, they would start, for example, they start with conservation of total spin or something, as a way of explaining this anti-correlation. Yeah, you get like a spin zero state, and then you measure spin at distant particles, and then by coupling of angular momenta, you get this anti-correlation. But this is an absurdly irrelevant aspect of the story. The entire point of Bell inequality is that it is a statement. It's a negative statement. It tells you that if you see certain patterns in your data, then no classical explanation is compatible with the universe. That is the statement. It has nothing to do with quantum mechanics. Quantum mechanics just tells us where to look, but you don't need to understand quantum mechanics in order to accept the conclusions of Bell's theorem. The best you should do is, before you even learn it, to forget everything about quantum. It has nothing to do with quantum. Well, nothing to do is a bit too strong, but it's a better side to err on than to talk about, coupling of angular momentum.
Okay, then just to finish up, we still have to resolve the joke from the very beginning. I guess I don't know if you've ever met Frank Wilczek or the other David Gross.
I have not, but I've exchanged many emails with the other David Gross.
Because somebody wrote an email to you.
Okay, yeah, maybe we should, introduce people to the background. There is, so by around the time I published my first paper, a Nobel Prize was awarded to David Gross, who's not me. and of course, there's been confusions ever since, and many funny stories happened. So when, for example, so I said it was around the time I started publishing. So at the time, the American Mathematical Society, they had a database of all the math papers, and they would match papers to authors automatically, and sometimes the algorithm would fail, and then they would write an email to the authors and say, can you please identify your papers amongst the following list? And so after I published my first paper, I got this AMS email, and the paper I had to decide I had to tell them whether it was mine or not, was the Nobel lecture. So that was the first time they got it. and then what happens is, so if you're a Nobel laureate, then many people want to talk to you, and so you don't put your email address on your webpage. And that means that whenever there's like a college being opened somewhere and they want to have a Nobel laureate as a speaker, they ask the secretary to invite David Gross, the physicist, and then they search the internet until they find the email address of David Gross, the physicist. And if I wanted to open an Indian college every week, I could. It's a bit an exaggeration, but I frequently get those invitations, and then I forward them to David Gross, and. Yeah, I have this heuristic. When I'm invited to a conference and the invitation says that I can fly first class, then I forward it to David Gross, because it's probably not. They probably.
Yeah. Sadly, also Edward Witten was not your PhD student as well.
No, but it is true that Google has this feature where when you put up like a person, then they will show the organic results, but then they will show this info box where they automatically summarize information about the person. And at one point of time, I have a screenshot when you Googled for Jens Eisert, there was a picture of Jens when he was young, and then there was a list of his PhD students, and the Nobel laureate was among that list. So that was funny. I think, by the way, so I told all my honorary stories how I always declined the invitation that I suspected did not mean me. I kind of suspected once I accepted David Gross. I didn't really probe, but once I think I accepted, and there's this event that Google organizes, or maybe it's no longer regular, but they had this sci-fu event where they invited all the biggest people in science to come to the campus on Google's dime and eat their good food and discuss. So they don't tell you why they invite you, because it should mix people. So I got this email from Google and say, yeah, we would really. I kind of suspected it didn't mean me, and then in my honor I wrote back saying, there's two David Grosses, but kind of implied that I would accept an invitation if it were in fact extended, and then they confirmed that they confirmed the invitation, and the other David Gross was not there. But of course, the most likely explanation is that they meant him, kind of were embarrassed and invited me anyway, and then the real David Gross didn't come. That was the one time, I think, where I probably took advantage of the similarity of names.
That makes a lot of sense. Who can blame you?
I could think of a few people. Yeah. Mm-hmm.
Okay, maybe it's
I have another David Gross story, but this is off the record.
All right, I think at this point we can probably stop. Thanks a lot for taking the time to do this. I mean, we got through a lot of content, and I hope that people will enjoy some of the conversation.